Good afternoon, everyone. In this video, we are going to discuss about the air masses, fronts, and middle latitude cyclones together with Miss Kimberly Gomez. Before we are going to proceed to our lesson proper, let's have first our learning objectives. At the end of the lesson, students will be able to describe the characteristics and source region of major air masses affecting North America. Next, explain the formation and movement of fronts, either cold, warm, stationary, occluded, and dry lines. Third, demonstrate how to plot and label frontal boundaries and low pressure systems on surface weather charts. Lastly, value the importance of accurate weather forecasting for safety and planning. So, what is air masses? An air mass is an extremely large body of air whose properties of temperature and humidity are fairly similar in any horizontal direction at any given altitude. A single air mass may cover more than 1,000,000 square kilometers. In this figure, it shows a large winter air mass associated with a high pressure area covers over half of the United States. Although the surface of the air temperature and dew point vary somewhat, everywhere the air is cold and dry, with the exception of the zone of snow showers on the eastern shores of the Great Lakes. Now, let's proceed to the source regions. In this slide, I will show you only the key points about the source regions, but still, I am going to further discuss each key points. So first is, source regions are regions where air masses originate. In order for a huge mass of air to develop uniform characteristics, its source region should be generally flat and of uniform composition with light surface winds. Third, the longer the air remains stagnant over its source region, or the longer the path over which the air moves, the more likely it will acquire properties of the surface below. Fourth, ideal source regions are usually those areas dominated by surface high pressure, which include the ice and snow covered Arctic plains in winter and subtropical oceans in summer. And lastly is the middle latitudes, where surface temperatures and moisture characteristics vary considerably, are not good source regions. Instead, the middle latitudes are a transition zone where air masses with different physical properties move in clash and produce an exciting array of weather activity. Now, let's proceed to the classification of air masses. Air masses are usually classified according to their temperature and humidity, both of which usually remain fairly uniform in any horizontal direction. There are cold and warm air masses, humid and dry air masses. Air masses are grouped into 5 general categories according to their source region, which I will show you a table later after this slide, 2 slides I mean. Air masses that originate in polar latitudes are designated by the capital letter P, which stands for polar. Those that form in warm tropical regions are designated by the capital letter T, which stands for tropical. If the source region is land, the air mass will be dry, and the lowercase letter C stands for continental, precedes the polar and the tropical. If the air mass originates over water, it will be moist, at least in the lower layers, and the lowercase letter m stands for maritime, precedes the polar or the tropical. We can now see that polar air originating over land will be classified CP on a surface weather map, whereas tropical air originating over water will be marked as MT. In winter, an extremely cold air mass that forms over the Arctic is designated as C, lowercase c and uppercase a, which stands for continental Arctic. Sometimes, however, it is difficult to distinguish between the Arctic and polar air masses, especially when the Arctic air mass has traveled over the warmer terrain. But when the air mass is colder than the underlying surface, it is warm from below, which produces instability at low levels. In this case, increased convection and turbulent mixing near the surface usually result in good visibility, cumuliform clouds, and shower of rain or snow. On the other hand, when the air mass is warmer than the surface below, the lower layers are chilled by contact with the cold earth. Warm air above cooler air produces stable air with little vertical mix. So, mauni siya ang table nga ako ang giingon ganina that shows the air mass classification and characteristics. So, as you can see in the source region column, which is in land, nasa duha ka ko ano. In land, it is continental, while in water, it is maritime. Then, diri naman po sa Arctic region, sa continental siyang nga row, it shows extremely cold, dry, stable, ice and snow-covered surface. Then sa maritime, kay wala siya nakabutang. Dili naman po sa polar, kung sa continental siya, it is cold, dry, and stable. While sa maritime, it is cool, moist, and unstable. Then lastly is sa tropical. Dili sa continental is, it is hot, dry, stable, air aloft, and unstable surface air. Then sa maritime, it shows warm, moist, and usually unstable. So in this figure, the principal air masses with their source regions that entered the United States are shown in this diagram, where are now in a position to study the formation and modification of these air masses and the variety of weather that accompanies them. So we are now finally in the air masses of North America. The bitterly cold weather that invades southern Canada and United States in winter is associated with continental polar and continental Arctic. These air masses originate over the ice and snow-covered regions of the Arctic, northern Canada, and Alaska, where long, clear nights allow for strong radiational cooling of the surface. Air in contact with the surface becomes quiet, cold, and stable. As the cold air moves into the interior plains, there are no topographic barriers to restrain it, so it continues southward, bringing with the frigid temperatures. While as the air mass moves over warmer land and to the south, the air temperature moderates slightly, even during the afternoon when the surface air is most unstable. Cumulus clouds are rare because of the extreme dryness of the air. And when the cold air dry mass moves over a relatively warm body of water such as the Great Lakes, heavy snow showers called as the lake effect snows often form on the downwind shores. So in this figure, it shows a shallow but large dome of extremely cold air. A continental Arctic air mass moves slowly southeastward across the upper plains. The leading edge of the air mass is marked by a cold front. We are going to focus on a special topic, which is the lake effect enhanced snows. During winter, when the weather in the Midwest is dominated by clear and cold polar or Arctic air, people living on the eastern shores of the Great Lakes brace themselves for a heavy snow showers. Snowstorms that form on the downwind side of one of these lakes are known as the lake effect snows. Since the lakes are responsible for enhancing the amount of snow that falls, these snowstorms are also called as lake-enhanced snows, especially when the snow is associated with a cold front or mid-latitude cyclone. Such as storms are highly localized, extending from just a few kilometers more than 100 kilometers inland. The snow usually falls as a heavy shower or a squall in a concentrated zone. So centralized is the region of snowfall that one part of the city may accumulate many inches of snow, while in another part the ground is bare. The contrast in temperature between water and air can be as much as 25 degrees Celsius or 45 degrees Fahrenheit. In this figure, we can see that as the cold air moves over the warmer water, the air mass is quickly warmed from below, making it more buoyant and less stable. Rapidly, the air sweeps up moisture, soon becoming saturated. Out over the water, the vapor condenses into steam fog. As the air continues to warm, it rises and forms billowing cuneiform clouds, which continue to grow as the air becomes more unstable. Eventually, these clouds produce heavy showers of snow, which make the lake seem like a snow factory. While in this figure, as the cold air moves farther east, the heavy snow showers usually taper off. However, the western slope of the Appalachian Mountains produces further lifting, enhancing the possibility of more and heavier showers. The heat given off during condensation warms the air, and as the air descends the eastern slope, compressional heating warms it even more. While in this figure naman, it shows two upper air patterns that led to extremely cold outbreaks of Arctic air during December 1989 and 1990. Upper level winds typically blow from west to east, but in both of these cases, the flow, as indicated by the heavy, dark arrows, had a strong north-south or meridional trajectory. The H represents the positions of the air-cold surface anticyclones. Numbers on the map represent the minimum temperatures in Fahrenheit recorded during the cold spells. As you noticed in this figure that rows of cumulus clouds are forming over the Gulf of Mexico parallel to northerly surface winds as continental polar air is being warmed by the water beneath it, causing the air mass to destabilize as the air continues its journey southward into Mexico and Central America. Strong, moist northerly winds build into heavy clouds with bright white in the white bright area and showers along the northern coast. In this way, a once cold, dry, and stable air mass can be modified to such an extent that its original characteristics are no longer discernible. When this happens, the air mass is often given in a new designation. So in summary, polar and Arctic air masses are responsible for bitterly cold winter weather that can cover wide sections of North America. This is also a special topic that focuses on the return of the Siberian Express. So, the extraordinarily cold air was accompanied in some regions by winds gusting to 45 knots. At least one news reporter labeled the onslaught the Siberian Express. The term has since become common in news coverage of cold waves in United States, although it does not necessarily mean the air mass originates in Siberia. During the first part of the month, continental polar air covered most of the northern and central plains. As the cold air moderately slightly far to the north, a huge mass of bitterly cold Arctic air was forming over the frozen reaches of the Canadian Northwest Territories. By mid-month, the frigid air associated with a massive high-pressure area covered all the northwest Canada. Meanwhile, aloft strong northerly winds directed the leading edge of the frigid air southward over the prairie provinces of Canada and southward into the United States. This figure, it shows where the sea level pressure at Miles City reached an incredible 1064 MB or 31.42 inch, a record for the contiguous states. An enormous ridge of high pressure stretched from the Canadian Arctic coast to the Gulf of Mexico. Also, as you can notice, on Christmas Eve, Arctic air covered almost 90% of the United States. As the cold air swept eastward and southward, a hard freeze caused hundreds of millions of dollars in damage to the fruit and vegetable crops in Texas, Louisiana, and Florida. Now, going back to the air masses of North America. The ocean water modifies these cold air masses by adding warmth and moisture to them. Since this air travels over water many hundreds or even thousands of kilometers, it gradually changes into a maritime polar or MP air mass. By the time this air mass reaches the Pacific coast, it cools. It is cool, moist, and conditionally unstable. Temperature readings in the 40s and 50s in Fahrenheit are common near the surface, while air at an altitude of about a kilometer or so may be at the freezing point. When maritime polar air from the Pacific moves into North America, it loses much of its moisture as it crosses a series of mountain ranges. East of the Rockies, this air mass is referred to as Pacific air. In this figure, it shows an over the relatively warm open ocean. The cool, moist air mass produces cumulus clouds that show up as tiny white splotches on a visible satellite image. In this figure, when a maritime polar air from the Pacific moves into North America, it loses much of its moisture as it crosses a series of mountain ranges. Beyond these mountains, it travels over a cold, elevated plateau that chills the surface air and slowly transforms the lower level into dry, stable continental polar air. In this figure, it illustrates a typical late winter or early spring surface weather pattern that carries maritime polar air from Atlantic into the New England in the Middle Atlantic states. A slow-moving cold anticyclone drifting to the east or north of New England causes the northeasterly onshore flow of cold, moist air to the south. So the winter time source region for Pacific maritime tropical air masses is subtropical Central and Eastern Pacific Ocean. Consequently, these air masses are often very warm and moist by the time they arrive along the west coast. In winter, the warm air produces heavy precipitation, usually form of rain, even at high elevations. The melting snow and rain quickly fill rivers which overflow into low-lying valleys, and the rapid snow melt leaves local ski slopes barren, and the heavy rain can cause disastrous mudslides in the steep canyons. In this figure, it shows a maritime tropical air, usually referred to as subtropical air, streaming into Northern California on January 1, 1997. So obviously it was New Year, no? The flow of humid subtropical air which originated near the Hawaiian Islands was termed as the Pineapple Express. Is one example of the feature known as an atmospheric river. Like a river of moisture far above ground, an atmospheric river transports huge amounts of water vapor from one place to another, typically from the warm, humid tropics and subtropics in the mid-latitudes. A typical atmospheric river is 400 to 600 km wide and a few kilometers deep. This figure, a powerful atmospheric river in early December 2012 brought more than 20 in of rain to parts of Northern California with wind gusts as high as 150 mm per hour. Atmospheric rivers also flow north from lower latitude to strike the central and eastern United States, such as the one that brought 10 to 20 inch of rain and devastating floods to parts of Texas and Louisiana in March 2016. While in this figure naman, it shows a surface weather map and the associated upper level airflow, or as you can see, the heavy arrow that brought unseasonably warm maritime tropical air into the central and eastern states during March 2012. A large surface high pressure area centered of the east coast coupled with a strong southwesterly flow aloft carried warm moist air in the Midwest and East, causing record-breaking March heat wave. So the only real source region for hot or dry is the continental tropical air masses in North America is found during the summer in northern Mexico and the adjacent arid southwestern United States. The air mass is hot, dry and conditionally unstable at low levels, with frequent dust levels forming during the day. Air must rise more than 3,000 meters or 100,000 before condensation begins. An upper level ridge usually produces sinking air over the region, tending to make the air also rather stable and the surface air even warmer. Now in this figure, it shows an instance where continental tropical air covered a large portion of southwestern United States and produced hot, dry weather during July 2005. So far, we have examined the various air masses that enter North America annually. Characteristics of each depend upon the air mass source region and the type of surface over which the air mass moves. So before we proceed to fronts and middle latitude cyclones to be discussed by Miss Kimberly Gomez, let's have first a brief review about the air masses. So an air mass is a large body of air whose properties of temperature and humidity are fairly similar in any horizontal direction. Source regions are air masses tend to be generally flat of uniform composition and in an area of light winds dominated by surface high pressure. Continental air masses form over land. Maritime air masses form over water. Polar air masses originate in cloud. Polar regions and extremely cold Arctic air masses form over Arctic regions. And tropical air masses originate in warm tropical regions. Continental polar air masses are cold and dry. Continental Arctic air masses are extremely cold and dry. Continental Arctic air masses produce the extreme cold of winter as they move across North America. And continental tropical air masses are hot and dry and are responsible for the heat waves of summer in western half of the United States. Then, maritime polar air masses are cold and moist. These air masses are responsible for the cold, damp, and often wet weather along the northeast coast of North America, as well as for the cold, rainy winter weather along the west coast of North America. Lastly is maritime tropical air masses are warm and humid and are responsible for the hot, muggy weather that frequently plagues the eastern half of the United States in summer. So I do hope that you have learned about the air masses. So Miss Kimberly Gomez will going to proceed on discussing the fronts and the middle latitude cyclones. Thank you everyone.
Fronts, transition zones between air masses. A front is the boundary or transition zone between two air masses of different densities, usually caused by temperature differences. This is where most of our weather actions happens, like rain, snow, thunderstorms. And a fun fact, the vertical extension of a front is called a frontal surface or a frontal zone. As you can see here in the illustrations, the vertical extent of two frontal zones, the polar front and the Arctic front. So the polar front boundary, which extends upward more than 5 kilometers, separates warm, humid air to the south from cold polar air to the north. So the Arctic front, which separates cold air from extremely cold Arctic air, is much shallower than the polar front and only extends upward on an altitude of about 1 or 2 kilometers. So if you can see here in the next picture, it shows a surface weather map with four different fronts. As you notice that the fronts are associated with lower pressure and that the front separates differing air masses. As we move to the east to west across the map, the front appear in the following order, like a stationary front between points A and B, and then the cold front between points B and C, and a warm front between points C and D, and an occluded front between points C and L. And let's examine the properties of each of these fronts. We have stationary fronts. Stationary front is a boundary between two air masses of different temperatures and densities that do not move or move slowly. So again, a stationary front is a standoff, a boundary between two air masses that barely move. So picture warm air on one side and cold air on the other. So with neither pushing forward. So these fronts can linger for days, bringing clouds like drizzles or light precipitation. On the colored weather map, it is drawn as an alternating red and blue line. Semicircles face towards colder air on the red line, and triangles points toward warmer air on the blue line. So the stationary front between points A and B, as you can see in the illustration, marks the boundary where cold, dense continental polar or CP air from Canada butts up against the north-south trending Rocky Mountains. And able to cross the barrier, the cold air shows a little or no westward movement. So the stationary front is drawn along a line separating the continental polar air from the milder, more humid maritime polar air to the west. As you can notice that the surface winds tend to blow parallel to the front, but it is opposite direction others on either side of it. Moreover, is you can see the upper level wind often blows parallel to a stationary front. Now we have cold front. A cold front occurs when a mass of cold dense air moves into an area of relatively warm, light air, forcing the warm air to rise. So a cold front is when a mass of cold, dense air pushes under a warm air mass, forcing it upward. So this results in a steep slope and is often associated with sudden temperature drops, gusty winds, and narrow bands of precipitation, sometimes with thunderstorm. The backdoor cold fronts come from the northeast and bring unexpected cold, damp weather, especially in spring. As you can see in the picture, the illustration, the cold fronts between points B and C on the surface weather map, as you can see in the screen, represents a zone where cold, dry, stable polar air is replacing warm, moist, conditionally unstable subtropical air. So the front is drawn as a solid blue line with a triangle along the front showing its direction of movement. On the closer look at the surface weather associated with the cold fronts situated in the southern United States, on the map represents the current weather at selected cities. So the station model used to represent the data at each reporting station is a simplified one that shows temperature, dew points, present weather, cloud cover, sea level pressure, and wind direction and speed. So the little line on the lower right hand corner of each station shows the pressure change, which is the pressure tendency, the weather rising or falling during the last 3 hours. With all of this information, the front can be properly located. As you can notice from the previous illustration and this one, so the precipitation patterns along the cold front might appear similar to Doppler radar image. So the region in color extending from northeast to southwest represents precipitation along a cold front. Notice that light to moderate rain, which is colored in green, occur over a wide area along the front, while the heavier precipitation, which is the yellow, tend to occur in a narrow band along the front itself. And then the strong thunderstorms, which is red, are found only in certain areas along the front. Previously, I mentioned backdoor cold fronts moving into New England during the spring. Notice that behind the front, the weather is cold and damp with drizzle, while to the south, ahead of the front, the weather is partly cloudy and warm. So cold fronts that move in from the east or northeast are called backdoor cold fronts. Typically, as the front passes, westerly surface winds shift to easterly or northeasterly and temperature drops. So here's the summarization of the cold front and the reference to summarize the ideal cold front weather winter in the northern hemisphere. Moving on to warm fronts. So warm fronts occur when a warm air masses advances and replaces a colder body of air, covering the colder air from the top and forcing the cold air out below. So as you can see in the illustration, a warm front is drawn along the solid red line running from point C to D. Here, the leading edge of advancing warm, moist subtropical air from the Gulf of Mexico replaces the retreating cold maritime polar air from the North Atlantic. So, as you can see, the direction of frontal movement is given by half circles, which point into the cold air. This front is heading towards the northeast. As the cold air recedes, the warm front slowly advances. So the average speed of a warm front is about 10 knots, or about half that of an average cold front. So during the day, as mixing occurs on both sides of the fronts, its movement may be much faster. So warm fronts often moves in a series of rapid jumps, which shows up in the illustration as you can see. Now, this next figure is a surface weather map showing the position of a warm front in winter and its associated weather. This next illustration is a vertical view of a model of the warm front, as you can see in the previous illustration. So if you notice of these two figures and observe that in the model, the warmer, less dense air rides up and over the colder, more dense surface air. This rising of air cold is what we call overrunning. Okay, so it produces clouds and precipitation well in advance of the front surface boundary. The warm fronts that separates the two air masses has an average slope of about 1 to 3, a much more gentle or inclined shape that than that of a typical cold front. Now, if we summarize the warm front, it happens when warm air advances over a retreating cold air mass. So, the warm air glides over the cold air, creating a gentle slope and widespread layered clouds. So, we have to expect light to moderate rain, snow, or freezing rain, sometimes well ahead of the actual front. Moving on to dry line, it separates warm, humid air from warm, dry air, specifically in Great Plains of the US. It's a prime spot of cumulus clouds and thunderstorm formation, especially in the afternoon due to surface heating, also called a dew point front. This illustration shows a well-developed dry line moving across Texas and Oklahoma during May 2001. So, like I said, cumulus clouds and thunderstorms often forms along or to the east of the dry line. This could develop as caused in part by daytime convection and a sloping terrain. As you can see, the Central Plains area of North America is higher to the west and lower to the east. Convection over the elevated western plains carries dry air high above the surface, so the westerly wind sweep this dry air eastward over the lower plains where it overrides the slightly cooler but more humid air at the surface. So this situation set up a potential unstable atmosphere that finds warm, dry air above warm, moist air. So in regions where the air rises, cumulus clouds and organized bands of thunderstorms can form. Now, moving on to occluded fronts. Remember that an occluded fronts form when a cold front overtakes a warm front. So this creates a complex boundary mixing the characteristics of both cold and warm fronts. As you notice, no? If a cold front catches up to and overtakes a warm front, the frontal boundary created between the two air masses is called the occlusion front, or simply an occlusion, or meaning closed off. So there are two main types of occlusions, which is the cold occlusions and warm occlusions. On a surface weather map, an occluded front is represented as purple line with alternating cold fronts triangle and warm fronts half circles. So both symbols point in directions toward which the front is moving. As you notice, no, the air behind the occluded front is colder than the air ahead of it. This is known as a cold type occluded front or cold occlusions. Now let's see how these fronts develop. Here, the classic model of developing cold type occluded front. This situation allows colder air to replace cool air at the surface. As a cold occluded front approaches, the weather sequence is similar to that of a warm front, with high clouds lowering and thickening into middle and low clouds, and precipitation forming well in advance of the surface front, since the front represents a through of low pressure, southeasterly winds and falling atmospheric pressure occur ahead of it. So the frontal passage, however, can bring weather similar to that of a cold front, like heavy, showery precipitation with wind shifting to west or northwest. And after a period of wet weather, the sky begins to clear, atmospheric pressure rises, and air turns colder. So the most active weather usually occurs where the cold front is just overtaking the warm front at the point of occlusions, where the greatest contrast in temperature occurs. So this classic model of developing warm type occluded front, as you can see, notice that the continental polar air over eastern Washington and Oregon is much colder than milder maritime polar air moving inland from Pacific Ocean. Observe that the surface air ahead of the warm front is colder than the air behind the cold front. So far, the ideas we have that I have presented on the formation of occluded fronts are based on the surface air temperature on either side of the front. Note that the air within the warm frontal zone is typically more stable than the air within the cold frontal zone. So the air behind the cold front is more likely to ride up and over the warm front than to flow beneath it. So for this reason, warm type occluded fronts are far more common than cold type occluded fronts. So in the world of weather fronts, occluded fronts are the mavericks. In fact, they may show up on a surface chart as a through of low pressure separating cold air masses. Because of this, locating and defining occluded fronts at a similar surface is often difficult for the meteorologist. So we have to take note that there are two types of occluded fronts. Okay, the cold occlusion, which is the cold air is denser and undercuts warm air, and then the warm occlusion, which is the cold air is less dense and rises over colder air ahead. So these are common in major cyclonic storms and can be tricky to locate on a weather map. Moving on to mid-latitude cyclonic storms. So these are large, swirling, low-pressure systems that forms in the middle latitudes and can bring severe weather continents. So they go through 5 stages in the Norwegian cyclone model. We have the stationary front, the frontal wave, the open waves, which is the pressure drops and wind spin, and then the mature cyclone, which is the cold and warm fronts develop, and then the occlusions, which is the system starts to die. Let's move on to Norwegian cyclone model. So if you track low pressure areas and temperature gradients where fronts form, especially in winter, you will often notice that these systems undergo a particular cycle. So this cycle results in what we are called mid-latitude or extratropical cyclones, which drives weather across the globe from fall to spring. So the Norwegian cyclone model is named to honor Norwegian meteorologists who first conceptualized the typical life of these cyclones in the 1910s and 1920s. Now we have the cyclone development stages. That's cyclone. Sorry for the typographical error. We actually summarize it all. The initial stage, which is the stationary front, and then we have wave formation, which is the frontal wave develops, the open wave, which pressure decreases, and then the cyclonic flow intensifies, and then the mature cyclone, which is the cold front approaches warm front, and then the occlusion, which is the front merge, and then the dissipation, which is the storm loses energy. I've already explained it earlier. Now, these are the critical formation factors, which is the upper air support, which is essential for cyclone development. And then we have the jet stream influence that provides energy and steering mechanism, and then the temperature advection, which drives vertical and horizontal motion. Now we move on to cyclogenesis regions. But when we say cyclogenesis, what does it mean? So this term used to describe any development or strengthening of a mid-latitude cyclones. It's essential the birth and intensification process of these large-scale weather systems. When we say intensification in the context of mid-latitude cyclones, it refers to the strengthening of the storm. So this involves a decrease in central pressure and an increase in wind speeds, leading to more vigorous and organized weather systems. So where do mid-latitude cyclones tend to form? So any development or strengthening of a mid-latitude cyclone is called cyclogenesis, which is I already mentioned. Certain regions of North America shows a propensity for cyclogenesis, including the eastern slopes of the Rockies. For example, so these storms often forms in areas like the eastern Rockies, the Great Basin, the Gulf of Mexico, and the Atlantic near the Carolinas. So again, this process of storm development is called cyclogenesis. Moving on to storm characteristics, we have potential energy conversion, latent heat from condensation, and surface air convergence. When we say potential energy conversion, so it means that the storms are powered by the energy that comes from differences in air temperature and pressure. So warm, moist air near the surface holds a lot of potential energy, which is the energy that is stored. And then when this air rises, the potential energy is converted into kinetic energy, which is the motion, fueling the storm. So how does it work? So warm air is less dense than cold air, so it rises, okay? As it rises into the cooler upper atmosphere, it speeds up, which is the kinetic energy increases. Then this rising motion can form towering clouds and violent updrafts, which are key parts of a storm. Then the faster and more organized the upward motion, the stronger the storm becomes, like in thunderstorms or hurricanes. And then we have the latent heat from condensation. So it means that when water vapor in the air condenses, which is turns into liquid droplets, it releases heat. So this is called latent heat. And this hidden heat adds even more energy to the storm system. So it works. How does it work? Warm, moist air rises and cools as it gets higher in the atmosphere. So when it cools enough, the water vapor condenses into cloud droplets. So during this process, the latent heat of condensation is released. So this heat warms the surrounding air, making it lighter, which causes more rising and further intensifies the storm. It's a positive feedback loop, like rising, condensation, heat release, more rising, stronger storm. So why is it important? Because latent heat is like a hidden fuel supply. It supercharges the storms from the inside out, especially in tropical storms and hurricanes. And then lastly, we have the surface air convergence. It means that convergence happens when air from different directions comes together at the surface. So this air has nowhere to go but up, and that upward motion is crucial to form formation. It works, how it works, like warm, moist air converges, which is they comes together to surface. Since it can't spread out, it's forced upward. As the air rises, it cools, it condenses, and forms clouds and precipitation. The upward motion strengthens as the air converges, as more air converges, feeding the storm system. This process is often triggered or enhanced by low pressure systems. So if we put it all together, the storm is a powerful engine made of these three parts working together. Warm, moist air contains stored or potential energy, and then air rises, converting potential to kinetic energy, and then condensation releases latent heat, warming the air and making it rise even more. And then the surface air converges, forcing more air upward, and then the cycle feeds itself and the storm intensifies. Moving on to memorable weather phenomena, we have a notable storm example is in 1888, the Children's Blizzard, and then the 1911 is the extreme cold front, which is at 75-degree Fahrenheit temperature drop in 2 hours. Let's move to atmospheric rivers. So this one transport massive water vapor quantities and can deliver 50% of annual precipitation with wind of 400 to 600 km and the potential for extreme flooding events. Jet stream roll strongest and most southerly during winter serious cyclonic storm movement provides critical upper level divergence or convergence zones, and then waves and westerlies we have long waves, short waves, and interact to influence storm development. So in the cyclone fuel, we have the jet stream and temperature. Mid-latitude cyclones are powered by, first is the upper air support, which is especially from the jet stream. And then we have the temperature advection, which is the cold or warm air moving horizontally. We have the latent heat from condensation and the surface convergence, which is coming together at the surface. So I have mentioned temperature advection. We have cold advection, which is the colder air replacing warmer air, and then the warm advection, which is the warmer air replacing colder air. So it drives energy conversions in storm systems. Northeaster's special cyclone type we have developed off eastern North American seaboard, fueled by temperature gradients between ocean and land, and can produce extreme precipitation and wind events. Note that the nor'easters, which is the strong cyclones off the east coast of North America, known as blizzards, coastal flooding, and high winds. For the key takeaways, weather is dynamic systems of interacting air masses. Fronts represents critical transition zones, upper level wind patterns crucial in storm development. So, to wrap it up, fronts are transition zones between air masses and key to predicting weather. And in the cold, fronts move fast and bring dramatic weather. The warm fronts move slowly but cover larger areas with gentler conditions. The drylands and occluded fronts are unique players in storm developments. And then in the mid-latitude cyclones are powered by upper-level winds, temperature contrast, and surface air convergence. Thank you so much for watching.